So my talk today is going to be about neutron and X-ray imaging, specifically tomography, and its application for the mechanics and physics of porous medium. So a quick reminder for those of you who aren't familiar with tomography, they're certainly familiar with radiography. So you go to the hospital, for example, you take a radiography of your hand. What you see are essentially the bones because they are denser. Tomography is the extension of this in 3D. You take a number of projections over a number of angles, and then it is possible to back project them through Fourier transform into a 3D object. Now, this 3D object is not just the bones, of course, it's everything that is inside. And it is most importantly, intrinsically just a 3D matrix, a 3D array of attenuation coefficients. Now, in the case of X-rays, this attenuation coefficient is proportional to the density, of course, but also to the atomic number of the atoms. That is because X-rays interact with the outer electron shell of atoms. The more the electrons, the higher the atomic number, the more opaque they will be. So as we go down the periodic tables, the element become more and more opaque, more and more visible. Neutrons conversely interact with the nuclei of atoms, which means that there's a number of very light elements such as hydrogen and lithium that are rather invisible to X-rays and are very visible to neutrons. And conversely, a lot of metals down here on the right that are rather opaque to X-rays and are instead quite invisible to neutrons. And furthermore, as we will see more in detail later, because we interact with nuclei, different isotopes can be distinguished. For example, hydrogen and deuterium. We'll see how this can be exploited for rock mechanics and physics. Just a quick introduction about how you make them. In the X-rays, it's relatively easy. You accelerate some electrons against a metal target, and through photoelectric effect, you make X-rays. Neutrons, one of the ways to produce them is, for example, through fission, like in an atomic bomb or a nuclear reactor. And specifically, one typically to do neutron imaging requires a spallation source or a nuclear reactor, as is the Institut Langevin, whose results I'm going to present to you today. Specifically, this one happens to be the reactor with the highest cold neutron flux in the world. That is for research purposes, and it happens to be in Europe, so in France. Grenoble specifically. So I mentioned briefly that some atoms such as hydrogen are rather transparent to X-rays and quite opaque to neutrons. What does it mean in practice? How is this relevant for rock mechanics and physics? Well, for example, let's take the simplest possible experiment. We inject water into a rock. Now, this is what we see in X-rays, and it is not much. You can kind of tell there is a front, but it's not obvious. Now, as we repeat the same operation in neutrons, this front is much more clear. And as a person that then needs to treat this data, I'd much rather treat the neutron in this case. Now, the experiment I've shown you is, of course, just a number of images, but as usual, the purpose is to extract quantities. For example, the position of the fronts, and therefore the speed of the imbibition. Once again, you might say, well, this is not a particularly exciting experiment in itself. It's just Darcy-law. It's nice and homogeneous. But of course, as we, for example, load triaxially our sample, there will be localization, and the fluid flow will be rather different. And sometimes the effect the localization has on the hydromechanics of the rock is far from intuitive. It is not just a mere role of the variation of porosity. There are tortuosity that comes into play, for example. And once again, as I mentioned, we can measure a speed field and correlate this with the strain field. How do we measure the strain field? Some of you might be more familiar with this. By comparing subsequent image through digital volume correlation, one can get a map of displacement of each or incremental displacement from one tomography to the next. And by that, we can, through continuum mechanics, deduce, for example, the strain field and correlate it with our fluid properties. Of course, we can get even more complicated. In this case, for example, is rock that has both localization features, the semi-vertical features, as well as natural inclusion. In this case, is a laminite. Now, I mentioned briefly before that hydrogen and its isotope are different. Well, in this case, hydrogen and deuterium, so it's a similar molecule, has the same number of protons and electrons, but has an extra neutron in the nucleus, have an order of magnitude difference in terms of attenuation, and so do their compounds. So water and heavy water, while being quite close from a physical and chemical standpoint, they have very different attenuation. And this can be exploited because all the images I've shown you are of water getting into a dry rock, essentially, which is interesting, but doesn't doesn't tell us the full story, for example, of a reservoir where we might want to push a fluid with a different fluid. Well, thankfully, after a first injection, in this case of heavy water, we can re-inject the second time with normal water, and we see that the fluid path is entirely different. In this case, the fluid almost completely ignores the sub-horizontal structures and shows up at the top and essentially just refills the cracks that had been emptied. Of course, these are all 2D images, but by acquiring a number of projection at different angles, one can reconstruct then a 3D volume of, for example, the distribution of the water throughout the volume. This was a simple case of purely hydraulic, but how about hydromechanics? Well, hydromechanics becomes relevant, for example, when we want to fracture this rock. So we inject water at very high confinements, as is the case for hydrofracking, and we break the rock. Well, in this case, one of the other advantages of neutron imaging is that it allows for a sample environment which are rather thick, corresponding to very high stresses, thanks to the opacity, to the transparency, of metals. And so we can impose, for example, about 70 megapascals. And as we inject the water at this high confinement, we can see in this case a subvertical localization and another one transversal to the borehole injection. Now, the second one was expected. The first one actually was an effect of the positional plane. So despite the existence of a notch transversal to the borehole, most of the water went orthogonally to it because that was the depositional plane, which was something that was not expected. Of course, we can also study plants, and here the reason why I show you this specific example of the study of a rhizosphere is because it's particularly fast. This is currently the world record of neutron tomography. It's about 1.5 seconds per tomography, and is particularly important when we have an intrinsically rapid phenomenon such as the water imbibition in a plant. I'm not going to bore you with all the other examples, but just to mention once again that thanks to the neutrons, we can go through rather thick environmental cells. We can inject, you can even see vapor injected into concrete, for example, or study, of course, the behavior of oil, which is also very rich in hydrogen as water is. But how about the converse? So we can, of course, also heat a geomaterial. In this case, would be a concrete. It's another porous medium, and study, for example, the moisture transport in the different types of concrete, as we can see here. And this is of particular importance to study the fire resistance of buildings, because depending on the speed of this front, we might have different amount of moisture accumulation ahead of the front, which can create a cork ahead of the front and prevent the vapor dispersion, and eventually can cause an explosive spalling, so an explosive expulsion of parts of the concrete which expose reinforcement bar, which eventually causes the collapse of the building. Similarly, we can also exploit other types of contrast than just hydrogen, but for example, studying the absorption of cadmium, which once again is somewhat transparent to X-rays, which is instead very, very visible to neutrons. And we can put some cadmium in a rock and try to see how many pore volume we need to inject to completely clean this rock. So I hope in this first part, I've convinced you that neutrons are quite different from X-rays. They have a different contrast. We can see a number of light elements, and they are isotope sensitive, which can be quite convenient in having, in being able to distinguish miscible fluids, and also that we can pass through a certain amount of metal. But the other important point I'd like to bring home is the fact that neutron X-rays are intrinsically very, very complementary. Where one fails, the other one can lend a hand, which is a bit the idea behind the instrument that I've had the pleasure to develop with some colleagues I mentioned at the end, to study, for example, porous media. So not just to produce neutron images, just X-ray images, but be able to acquire both techniques simultaneously of the same rock. I'm going to give just a couple of relatively quick examples. This just to mention that we are currently going in upgrade, which will last until the end of the year, that will add a number of options. One such example is hydromechanical couplings. For example, Calovox-Fordian clay rock is particularly important in terms to store nuclear material, and this is what happens when we expose them to water. It's a rather violent reaction. I reassure you, it is an outside condition. There's a lot more confinement inside conditions, but you can see immediately that the hydromechanical coupling is very strong. So at the top, you can see the X-rays, which capture very well the opening of fissures, and the water can be captured by the neutron underneath. And of course, depending on the bedding plane of the two rocks, this behavior will be entirely different. Once again, the purpose here is to quantify something. In this case, is the opening of the fractures and the invasion of the fluid. And what we discovered is essentially the fluid invades a small amount, it opens all the way the cracks that then stabilizes across time. And once the structure are open, these are the driving mechanisms that will bring the water all the way across. In following experiments, we repeated the same operation in confined condition, and we managed to even compensate for the deformation of the rock. So we could really very accurately quantify the amount of water imbibed into the rock and correlate it with the strain, in the incremental strain as deduced by the X-rays. Going back to the same example of the heating of concrete, I want to give you an example of how neutron X-ray can also be essential for segmentation. So to distinguish the different components that make part of a rock. In this case, is an artificial rock, it's a concrete. And you can see how neutrons are excellent at distinguishing aggregates from the cement paste, but it's hard to tell apart the aggregates from the pores. Conversely, X-rays are excellent in finding the pores because they are much more transparent than cement and cement paste and aggregates, which are instead quite similar. So it's only through their combined use that segmentation, so the univocal determination of all the phases composing them, are absolutely essential. To do this, we develop a number of tools, notably an expansion of digital volume correlation to compare not just commensurable fields like X-rays to X-rays, but to compare X-rays to neutrons. And as a byproduct of this, beside the exact subpixel alignment of these two volumes, it's also possible to do a rigorous segmentation. Furthermore, in this case, once again, the X-rays provide essential information about the evolution of the microstructure, in this case, the opening of fissures because of heating, and the neutrons provide information about the effect that this has on the moisture transport caused by the heating. The analysis can get relatively fancy. For example, we can look at the neighboring area around the fracture to see how deep transversely to the fracture does this drying take effect. And we observed an effect of the drying up until 4 millimeters away from the fracture, which is almost twice as much as what our previous models seem to suggest. Just to bring another couple of examples quick examples of possible application, haloclasting. So brine will get into a rock, in particular in coastal area, the water will evaporate, the salt will accrete, and eventually the salt can cause opening of fissures. And once again, fissures are best studied by X-ray imaging, but the salt in itself is rich in chlorine, which is somewhat transparent to X-rays, whereas it's very opaque to neutrons. So once again, this coupling can be ideally studied by these combined techniques. Or wormhole dissolution, we can do a number of tomographies as we inject acidic water, study the fingering process or the development of these fingered wormholes with the X-rays. But this is highly coupled with the fluid flow. Of course, is the fluid flow solely passing through these fingers, or are those fingers just where more acid passes through one? So we can acquire a number of X-ray tomographies as we inject acid, and every once in a while we can inject, as we will see in a second, different fluids. So, for example, these were heavy water saturated, and we inject normal water to be able to see what is the flow path. And in this case, we see that essentially the flow path is the water solely goes through the main fingers until it comes out on the other end, and it plumes out, where it creates a new, it will seek and create the new finger structures. Of course, neutron can be used also to study, for example, corrosion, once again, very hydrogen rich, or to study and seek organic rich materials, as in the case, for example, of fossils. This is just a quick slide to point out the fact that I have only made examples about hydrogen or essentially porous media, but neutrons have these neutron X-rays combined together have unique possibilities also, for example, to study batteries. In this case, the evolution of the microstructure in X-rays and the lithium distribution through neutrons. Okay, this one I can perhaps skip. To finally conclude, this was, I hope I convinced you that there are some tremendous possibilities of the combined use of neutron and X-ray imaging. The combination of these two techniques is relatively recent, only since the last 3 years, essentially. In terms of spatial temporal resolution, I haven't had time to get into the details, but The current boundaries of what's possible are being pushed. We are currently around 3 micron spatial resolution, and tomography can go as fast as 1 second. Not unlike X-rays, the purpose of all these images is not just to have pretty pictures and have a qualitative understanding, but to extract quantities about the incremental strain field, the water concentration, and so on and so forth. And there's much work to be done, but there's also a lot of fun to be had. Hopefully, I've skipped a few things, but if you're interested, there's a number of reviews about specific domains you can find here. And of course, if you're interested about the specific instrument, do feel free to contact us. And I couldn't mention every person we collaborated with to make this result, but for sake of brevity, but here are some of the more important ones.